The file system interface, because most of you have been using the files, the operating systems for a long time now, and you know how a file system interface looks like and what it does for you. So the basic idea is that you have the contiguous logical address space. As I said earlier, that there are logical units, logical blocks inside the storage media, and these are contiguous, meaning they start from 0 and then 1 and 2 and simply they go on, and we don't worry about where they're stored physically. And the file can contain data or it can contain a program. The file is a collection of contiguous logical address space, right? So the block numbers that we are talking about, so if you collect a group of block numbers, that group can be called a file. So, and the contents of those that file could be either data of numeric type or character type or simply binary type, or it could be a program that could have instructions that can be sent to the CPU, or first it will be loaded to the memory and then sent to the CPU. The contents defined by the file's creator could be of many types, like text file, source file, executable file, because in the binary format you are able to define your own file format to have your program read data in a specific format that only your program understands, right? So that allows for infinite number of file types that you can create. And so there are some attributes that each file has. The first one is name, and then the identifier, which is the unique tag which identifies the file within file system, right? So these are two different things, because the file is a physical entity which physically exists on the surface of this physical media somewhere, but there is separate things stored on this physical media, which is the managerial information about all of this data about data, that will have to know the identifier for this file in order to access the file instead of the name. So it is just like program name was a file name when we studied programs, and the PID is its identifier number. Just like that, we have a file identifier as well. Then there is file type, then file location, then file size, and then the protection information, like who can read, or like user rights to the file, and then there are time and date and user identification, all of these kinds of stamps on the file, which tells you when the file was created and when it was modified, etc., and information about files. So these things are slightly different. So all of this information about the files, where it is stored in the directory structure, which is maintained still on the disk alongside the files. Many variations, including extended file attributes such as file checksum. So these kinds of attributes allow you to check the files for errors, and again this information is also kept in directory structure. So directory structure is the main location where all the information about the files is stored, which logical block numbers this file contains, and what is the name of the file, what is the ID of the file, what is the type, location, size, and other information of that file. These are all stored in the directory structure. How files are grouped together inside a directory, this is also stored in the directory structure. So in the Mac OS, you can see that these are the attributes, like what is the type of the file, and what is they call it kind over there, and then what is the size, where it is stored inside the directory structure, when it was created, when it was modified. And similarly, there will be some privilege information, like the access permissions, like who is able to read and write to the file, who is able to only read to the file from the file, or who can access the file. So similarly in Windows, there is similar attribute windows. And similarly, file operations, operations that we perform on files, we can create a file, write, read, reposition within file, delete, truncate, or open or close the file. So these are different operations, very obvious, because file is an abstract data type, because it contains of logical numbers, and that's it. So when you ask the operating system to create a file, it is going to find free logical blocks on the surface of the storage media, and it is going to create a new entry inside the directory structure that I'm going to allocate these logical blocks uh, to this newly created file. Similarly, you are able to write to this file or read from this file. And by the way, these read and write operations, you have to use the intermediate interface of memory for that. So all the data that you request to write first goes into the memory, and then the operating system is responsible for taking that data from memory into the disk to the desired location where the directory structure is pointing for the logical blocks of that particular file. Similarly, read operation is similar, and all the data from the disk is going to be read by the operating system into the memory based on any read or write pointers which point to the logical blocks of that file, which are already, as I said, are stored inside the directory structure. So similarly, you can reposition within the file, just like, for example, in the cassette players from the old days, that you had to rewind or forward the amount of tape. It is like repositioning your head on top of that magnetic tape. And similarly, you're able to delete the file or change its end location, truncation. And similarly, you can open the file, which brings the file into the memory, or you can close the file so that it is backed up on the hard disk again and it is closed from memory or removed from the memory. So whenever multiple files are opened inside an operating system by different processes, the operating system maintains an open file table to track the open file. So for example, in the operating system right now, there are 100 files open. So the operating system is going to maintain an open file table, and there will be a file pointer which points to the last read write location per process that has the file open. It is just like the program counter that we saw in the processes part. So just to keep track of where you were the last time a process accessed this file, the file pointer will point to that. And similarly, file open count is the number of times a file is opened by different processes. So for example, multiple processes, it's a read-only file and multiple processes are reading this file. And similarly, disk location of the file, cache of data access information. So the directory structure is going to be cached into the memory for faster access to the disk. And similarly, access rights will also be maintained about the open files, so that it's easier to protect the files from invalid access. So this is all we do with the open files. And then of course, because an open file can be a shared data, so you need to apply locking to that. So you always see that, for example, you are accessing a file inside the Microsoft Word, and you are trying to open the file in some other in other application. So the application would say that this file is already open in some other process, so I'm not able to open this file. So that is the locking mechanism, just like we saw in the synchronization chapter, that you can have semaphores or mutexes that allow access to a shared data. So those locks are also implemented for the so here they say the shared lock is similar to reader lock, and the exclusive lock is similar to writer lock, that we already studied in the synchronization chapter. So sometimes it is mandatory. For example, the file is when you try to open it multiple times, it will deny access. And sometimes the lock is advisory, that you are allowed the opening the file in multiple locations, multiple processes, but it warns you that it is not advisable to do that. Then there are so many different types that you always see inside your operating systems, like the txt file, or maybe jpg file, or avi file, or so we see all of these files so many times when we are using the operating systems. So then there is file structure. So if there is no file structure, then it is just a sequence of words or bytes, and you are responsible for deciding which part will represent what. So for example, when you study the, I just recalled that when you study the format of JPG file or AVI file or TXT file, so the first few bytes inside these files, they represent different kind of information about the file. For example, in the JPEG, it tells you the compression information and different types of information, that what colors are being used in the image. It is also stored at the beginning of the file. And what is the resolution of the image, what is the size of the image. So all of these informations are stored at the starting of this JPEG file. So also called the header information. So the header information is actually part of the data file, but because we knew that it's a JPEG file, we know that there is a standard way of storing JPEG file, and the starting location, the starting bytes are going to tell information about the data. So also sometimes called metadata, right? So it's data about data. So but from the perspective of a physical storage, it is not different, any different from simple bytes. So these are simple bytes, but they represent something that we know. We have a priori knowledge of what those bytes represent, right? So simple then there are simple record structures like lines, fixed length or variable length, and then there are complex structure which are formatted documents, like as I told you, JPEG can be simulated by inserting appropriate control characters. Who decides the structure? The operating system and the program. So the operating system would definitely decide the file structures for the file types which are well known, which are used by the users and the operating systems alike. So the operating system is going to give some kind of documentation or tell you that this file type should have this kind of structure inside. But most of the times programs, they decide what would be the structure of the file, right? So we see new file types emerging every day. Actually, it's really easy for you as well to write a program which defines a self-defined type and then manipulates the data accordingly. So sequential access file is something where the pointer points to one location and you simply tell the pointer to go forward in one direction or reverse into another direction. So for that, the system calls are simply like read next or write next, and then resetting takes you to the first starting location of the file. And then there is direct access, random access you can also call it. It simply tells the operating system to read the actual number of the block that you want to read, or write to which block, or position your head to which block and block number, and then use the sequential access type, which is read next or write next. These are really, you can say, logical or obvious kind of mechanisms to read or write to files. And so this is how you read next. You simply read the current pointer and then you increment the current pointer by 1. And if you want to write to next block number, you simply write to current pointer and then you increment the current pointer to go forward. So other methods, other access methods are one of those are called and they're built on top of base methods. Like these methods may be the lowest level methods that are implemented to access logical blocks, but on top of those, using those base level access methods, you can define higher level of abstraction to access logical blocks. So you can visualize your blocks as a tree or as an array or as a two-dimensional array. All of those methods can be implemented using these base methods. So let's look at those. The first one is index. For example, you wanted to create a file that contained these kind of records, like there would be last names. So all the records will be sorted with last names, and there will be logical record number, and for each record number there would be a separate file. So the file that saves the records is called the index file. So it provides indices to the relative files, and when you go from one index file to the relative file, inside the relative file there is going to be more information about that record that you wanted to access. So this would be, so these are two separate files. The index file and the relative file are two separate files. This is a, you can say, a higher level access method for to read files. And similarly, the directory structures, so this is only one example of a higher level of abstraction for access methods. The directory structure itself, it is slightly different thing, which is, again, as I said, this is your disk, and inside the disk there are different logical block numbers. How does the operating system know, and who will tell the operating system which logical block numbers? For example, I say that these logical block numbers are one file, right? So there will be a kind of record management system on the disk as well, in the corner of the disk. And the evidence for that is that whenever you buy a storage device and you try to write to that storage device, so when you try to access the files, you can only use slightly less amount than you bought the disk for. For a terabyte disk, if I bought a disk of 1000 gigabytes, so I will maybe get 970 gigabytes of data. So where did the 30 gigabytes of data go? That 30 gigabytes data actually went to the directory structure, right? So because it is in storing the information about 970 gigabytes of these blocks, so that will be called the directory structure. This thing will be called the directory structure. So the directory structure will contain all the information about files. For example, this file contained like 100 logical blocks, so all those logical blocks starting from the first one will be stored inside this directory structure, and in one way it will be pointing to that file, right? So you can say this directory structure is this node in the directory structure is pointing to this physical file on the disk. So in order to elaborate the directory structure, first we need to know what disk structures are. Disk can contain multiple partitions, and they can either be used raw or they can be formatted with a file system. So partitions are also called, or they can be known as mini disks or slices, and every entity containing file system is known as a volume. So the difference between a partition and a volume is that a partition may not contain a file system, it may be raw, but when you write a file system on it, it becomes a volume. So these are just traditional names for these things. So per partition becomes a volume when formatted for a file system. So each volume containing file system also tracks that file system's information in device directory or volume table of contents. So these are, again, as I said, names for supporting things to the directory structure. And as well as general purpose file systems, there are many special purpose file systems. So let's have a look, and this is the picture for one physical disk divided into two partitions, and this is the example of two physical disks combined into one partition. So both of these things are possible. And then the types of file systems, these are different file systems, and again, as I said, they are different. Like, for example, there is TMPFS in Solaris. These are all Solaris file systems. These are all special purpose, you can say, file systems which are defined by a particular operating system. So operations performed on the directory, you can search a file for a file inside the directory structure. You can create a file. So as I said, so if you're searching for a file inside the disk, if I ask you guys, what do you think? Will we be going into this part, or will we be going into this part? So for example, this was a 1 terabyte hard disk, and 970 gigabytes were over here and 30 gigabytes were over here. Then the searching is done in the 30 gigabyte area, which is the information about the files, and you just need to look in for names or file sizes. So you may have done file search. So all of this will be done inside the inside this the directory structure. So you don't need to go inside the data, because anyways, in going inside the data will be useless, because all of these logical block numbers are absolutely looking the same, looking like they're just the same things repeated over and over again. The data inside will not tell you anything at all. So, by the way, and that actually reminds you of the very important fact that if you somehow lose this data, your files will absolutely become useless and they will disappear. You can never retrieve your files if you have lost your directory structure. So directory structure is an extremely important thing from that point of view. So okay, so now the directories you can operations you can perform on directories. You can search for a file, you can create a file, you can delete a file, list a directory, rename a file, or you can traverse the file system. And the directories are organized to for efficiency, like you're able to locate a file quickly yourself, because you can see the directory structures. You can see which directories, you can name them, so that it's easier. Like for example, I have a work folder which I've been using for like decades now, because whenever I start this any computer, so I simply go to this work folder, and in the work folder I have like all of these different things that I've been doing. And then there are grouping, like logical grouping of files by properties. For example, all Java programs or all games. This is also possible in directory organization. And in the previous life of computers, we used to have single level directory, where one directory only contained one file, but suddenly it became slightly different, and we allocated different group of directories to different users, and that was called a master file directory, and the scheme was called two level directory. And then suddenly we came to the tree structured directory, where we had subdirectories, and inside subdirectories we had multiple files, and each file would be pointing to the logical blocks that it contains. And sometimes, even multiple directory locations could be pointing to the same, you can say, physical files for optimization. And then these are different commands you use to modify the directories inside Linux, like rm to delete a file, mkdir to create a directory, and stuff like that. And you already know the cd, which is change directory, to navigate to different subdirectories in order to access files. And then there are acyclic graph directories, where you sometimes have cycles. You actually prevent cycles, but here you can see that the count subdirectory is pointing in both the which are both owned by the dict directory and the spell directory. They're pointing to the same file, but this is not a cycle. These are both ending at this node, so there is not like a reverse arrow here, so that we can say that acyclic. This is there where there's no cycle. So we can have shared subdirectories using acyclic graph directory structure. It allows for optimization. So for example, this is a 500 megabyte file, and the user copied this file from this to this, but you physically didn't make a physical copy on the logical blocks of this file. So for example, this was the 500 megabyte file. You didn't physically copy all these blocks over to some other location inside this 970 gigabytes area. You simply copied the address in this location to using a couple of bytes. So the file is simply copied. So there is another option that what if this collection was modified, then obviously you will have to maintain an information. This is a general graph directory, so any arrow is possible going from any location to any other location. So these are different types. So these are methods to reduce or to eliminate cycles inside the general graph directory. Again, as I said, that cycles may not be really useful, so we delete the cycles. So this is another thing which is called file system mounting. So let me show you. This is something. This is an external hard drive, right? So just to jog your memories a bit. So this is a hard disk drive. This is external drive. So you connect it with this, what we call the USB cable. So do you think, as long as this is in my hand, so does this contain a file system or not? As long as this disk is residing on my desk, on a table, it contains a file system, but that file system can only be accessed when it becomes part of the active file system of an operating system. So right now I'm using this Windows session, and this Windows session is an active session where the file system is also loaded inside the memory of this operating system, so that it can access any disk which is connected to this computer right now. So as soon as I connect this external hard drive to my computer, that file system will be if I want to access that file system, I will have to make that file system part of my existing file system of my operating system, which is running as I'm using the computer, right? So the process of attaching or adding a new disk to my operating system file system is called mounting. So whenever I insert any for example, I have this thing. This is also a tiny disk in my hand, right? So this is a memory card. So as soon as I so let me show you actually. So if in case of Windows, it is much easier because they have really done it in a good way. So these are my disks right now, and they are full, by the way. And so as soon as I insert this memory card inside the system, it is going to be mounted and made part of the this. So here you can see this is a new partition G. So what the operating system did right now, it mounted this this file system with the existing file system. So the Linux does it in a slightly different way. It uses a subdirectory to show the contents of this card. It doesn't make separate partition, but again it is mounting to a different point. So in the Windows mounts to the, you can say, the root. There are some extended things like how to protect your files. So the file system provides and obviously you could simply, you could see that it may not be very difficult to implement. You simply need to add some data in the file, in the directory structure, that who can access the file in what way. So these are simple checks, if else kind of checks, which can be applied. And similarly, this is a Windows 7 access control list management window, in which you can see that you can select a user, and then you can allow or deny permissions of different types of access for that particular file for which this window is opened, like for listpanel.java. You can select a user, and you can specify which types of access are allowed and which types of access are denied. And this is how the user modifies the information in the file structure. So what this window is saying, that the user is able to change the attributes for this file in the file structure using this window. Okay. And these are like UNIX directory listing, in which it is also showing different types of attributes like file size, file timestamps or dates, and different access or user information, right? So again, as I said, this is highly user dependent, or the operating system designer dependent, what they want to implement.